overview. The last time we started to look at the implication of developing a highly complex models and then a very simple models that can just that may not be able to really capture the entire dynamics of the disease. Now, and then we're comparing between the aircraft and the bicycle, and we mentioned that now if you are going to produce a realistic models, it takes time. It takes more time because this will involve very high computational power, and then a lot of things are going to be put in place for you to produce that. Now, most of the model we are developing, like I told us the other time, theoretical models, if you sit down now under the next 15 minutes, 20 minutes, you get the result out and then you are publishing within the next 2 weeks. So, but for this kind of models, you need a lot of things. And then you also need to talk with the people in the programs, like the public health specialists, and then you are giving them feedback from time to time, and they are seeing the possibility of what you are talking about. So it's not something that you just come up and then you gather something together and then you throw it into for publication. It takes time. So now the same way building an aircraft will take a lot of time because people are involved. Now in this kind of model, human beings are involved. If you are any decision you make in terms of you are saying this is the optimal intervention, it's going to affect some population. So if your model output is wrong, then it means that the government may end up wasting money. You understand? Because you have advised them that this is the optimal intervention, and at the end of the day, the intervention did not give optimal results. So in the long run, they will have wasted money. Next time, they will not listen to you. So you need to be careful when you are dealing with this kind of operational modeling. Now, if it's academic modeling, you publish, nobody question you. You are in your house drinking your tea and all of that. Nobody is using that because it doesn't have anything to do with anybody. But when it has to do with data that represent a population, you have to be very careful. Thank you. So now, similarly, which sort of model is the appropriate depends on the precision or generality required. You know, now the requirement comes from the programs. People who are in the programs, they begin to show you their need, what they need, the questions they want to answer. So it's not something you just quickly sit down in your table and develop and write something. It takes time. You have to build it. You have to build some complexity into it and all that. So the available data, what kind of data is available, is very important in this situation. And the time frame in which the results are needed. I mean, sometimes maybe 2 years ago, 2023, Malaria Consortium, they approached me that I should develop a model. They want to present for Global Fund and all of that. And what they asked me to do, there was no funding attached to it. And then they had the funding. So I said, okay, so it's monkey they walk, baboon they shop. So then I'm not going to do because it's going to be intense. I have to have sleepless nights and then with my student. That's number one. Number two was that they are asking for like 2 months. 2 months is not possible to produce that kind of model that people will make decision on. I said it's not feasible, and then everybody have to go his own way, because if you have to do that kind of job, you have to test run it over and over again to be sure, because this is not, you are talking about global stability. Although no, that's not it. They are making decision. They want to know whether what you are saying, is realistic. So at the end of the day, if you are going to give something like that to such people, it takes time, at least like 3, 4, 5 months, that kind of thing. Not just 2 months and then we are rushing. A lot of things can mix in the whole process. So by definition, all models are wrong. That was what George Box said. What do I mean by wrong? Because they said there are assumptions. Every model has some level of assumption. It's not wrong per se, wrong not in the sense of not being useful, but wrong in the sense of that every model is limited by its assumption. Now, in the sense that even the most complex model makes some simplifying assumptions. Realistic model, they still make assumptions. So it is therefore difficult to begin to say, to express definitely that which model is right. But we are going to talk about that in terms of what makes a model to be good or right or useful. So though naturally we are interested in developing models that capture the essential, I want you to underline what I want, essential features of a system. Now, developing models that capture the essential features of malaria, essential features of cholera dynamics, essential features of COVID-19. There are certain things, just like we have been saying, that if you are developing a model, you are saying so simple, simple but not so simple and all of that, like the law of parsimony we are saying. But that does not mean that certain principles of the disease dynamics should be left. There are certain things that now if you are developing a model, the biology of malaria is left behind. That will not speak to anything. So ultimately, we are faced with a rather subjective measure of the usefulness of any model. Usefulness. How is this model useful? Can we use it for anything? Please, it's not moving. It's not moving. The slide is not moving. So usefulness. Is it useful? Is this model useful? The outcome of this model, is it useful? Can we use it to make any prediction, or can we depend on it to make policy? You understand? So we need to think about that. These are things that we need to look at in terms of okay, so why model? Why do we model? Why are we trying to model? Now, one of the reasons is we need to plan for outbreaks. Like we're talking about early warnings. Now, models can provide warnings ahead. And this is going to happen if you don't do anything, you are likely to have this. Like I'm giving a forecast. In the next 1 year or 6 months, these are the likely things we can see. If the government failed to do the right thing, you want to remain at business as usual, then you discover that we are going to have maybe an outbreak of disease, and then that is going to affect the economy. It's going to affect everybody from traveling. The travel. So it means that when it affects travel, some certain business are going to be affected. Some people are not going to make. During COVID, look at it now. So many people who are involved in aviation business, they lost a lot of money. In fact, some of them downsized because they were not doing anything. So money was not, so you see the effects when there are outbreaks, when there are disease. You cannot go anywhere, especially the one that is global or pandemic. You can't go anywhere, even if it is local epidemic. Now, there are countries that will list your country as, please don't come to us. Yes, don't come to us. I don't know. There was Ebola. During Ebola, so I entered. I went to India, and as soon as I entered, they told me that, okay, you are from Nigeria, okay. I think I was the only Nigerian in that flight, so they just put me somewhere. You are not going to enter. Yes, they needed to carry out a test. It's a big shame. You now hang somewhere until they finish the test, they check everything. That's when they release you to the population. Or else, from there, they send you back to your country. Yes. So that's the implication. So you find out that a lot of travel restriction can come on certain countries because they feel that they don't want your problem to be transferred to their home country. So you sit down in your country. You don't go anywhere. So, and this can affect research. You understand? Affect collaboration, affect networking, and all of that. So, in fact, there are some travel you want to make. When they look at your visa, oh, you have visited this country. During COVID, now they were checking that, okay, which country have you visited? You visited Turkey. Okay, be here. Especially those countries that have burdens. You visited China. Stay here. They just put you there. Yes. Are you getting me now? So, like that. They just put you there that, okay, if you have visited this country, you can't enter our country for now. So those are the things that, limitations. So in trying to model, we want to plan. You need to plan for outbreaks. Then in the planning, we want to look at what's the speed of the spread. the speed of the spread of the disease. You are trying to look, just like the velocity time graph I plotted yesterday, I wrote yesterday. So, and then you also want to look for how severe is the disease, the severity of the disease. How severe is it? Those are the things that is coming into the mindset of the programmers, people in the program, public health program. Now, intervention effectiveness. What are the available control interventions that are effective to control, to bring down the disease? Do we have them? And then, what kind of model do I need? Now, that depends on the question you want to answer. The kind of model you need depends on the kind of question you want to answer. Now, statistical models are there, dynamic or mathematical models, health economic models are there. And then, broadly speaking, there are mathematical models aimed at facilitating our understanding of the medical, biological, ecological, social interaction that manifests the outbreaks and epidemics of infectious disease in order to gain insight into specific questions or to generate theories about what must or might happen. That's future. Now, understanding the medical aspects of the spread of the outbreak, like take for instance infectious period, is medical. Infectious period. Now, you cannot use incidence data to estimate infectious period. It's not possible, because that's medical and biological. You cannot use cases, incidence cases, reported cases, to estimate recovery rates, incubation period. You can't. You can't use them, because those are biology. So you need to understand now the ecological aspect of the disease. Take for instance the mosquito population interaction, and that was why you see we are talking about One Health. One Health approach. You have to look at disease in that direction, how it's affecting the zoonotic, that's zoonotic in terms of animal, and then the human disease. There are a large number of disease that comes from the animal to human, right? So you need to also understand social interaction. What impact are they having on the epidemics of the outbreaks? Now, and then all of these help us to gain further insights. Now, are there statistical model aimed at capturing the data generation process? Do we have for detecting general patterns? You want to look at the pattern of just like what we are saying yesterday. We are trying to decompose the signals we are seeing in a number of cases. I don't have this thing here. Okay, yeah. So now I'm seeing a signal like this, but I don't fully understand this signal. I don't know this signal. So I need to subject it to either additive decomposition, some level of decomposition, or what we call STL, that's seasonal Lewis. So where I'm going to have all of these signals in different components. I'll have the time trend component, the seasonal component, the cyclical component, and then the remaining part which has to do with random error. Yes. So now, looking at that, so also predicting epidemic trajectories and then managing control strategies. So within both mathematical and statistical models, there are models designed at the population level in a phenomenological way versus models that are individual based. Now, which researchers aim to capture relevant mechanistic processes, like the one I was saying yesterday, when you are looking at individual based model, which you also call agent based, you have to capture each person in the population, and that is computationally intensive. So individual based models start from the description or assumption about the evolution of the infectiousness and the natural history of disease progression within an infected host. So in an individual-based model, there are so many things that are captured. Apart from, take for instance, malaria, you are looking at the malaria dynamics, the population dynamics of malaria on its own. And then you look at the interaction between malaria and human. And then you look at also the aspect that deals with the within host dynamics. Within host dynamics in the sense that now, both in the mosquito and in the human, because in the human, the sexual phase of development of the parasite take place, asexual phase of the development of the parasite. The parasite dynamics takes place in different ways in both human and mosquito. The mosquito, you have the sexual phase. In the human, you have the asexual phase of the parasite dynamics. So these are things to look at, because now mosquito does not just say that he wants to pick blood. There's a reason why he wants blood. He's trying to oviposit. There's oviposition. He wants to lay his egg. So in trying to lay eggs, he needs blood. Are you getting me now? So at that period, at that particular period, now there is a dynamics that follows. Because in trying to lay eggs, it seeks for human being, and then when it gets you through your CO2, you breathe out, it locates you, and then it tries to feed on you, right? When it feeds on you, it's able to lay the eggs on. Mosquito can. They have these kind of they have very, 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 very fuzzy behavior. Fuzzy in the sense that, in laying their eggs, some like marshy areas, some like, that's why I said you have, for Anopheles mosquito, we have about 30 species of them. Are you getting what I'm saying now? Anopheles gambiae, Anopheles phonestos, a lot of them. There are some of them that are particular to certain region. In Nigeria, we have mostly gambiae, phonestos. There is one they call Anopheles Stephenson. I don't know whether you have heard about that. That is coming from the East Africa. That one is more dangerous. So if it enters here now, we'll be having other cases. Is somebody talking? In the hospital? Okay. Now, this includes models for the latent periods. The latent period, the infectious period, the incubation period, the recovery, mortality, and so on. So, and then some individual-based model also combine social contacts with the evolution of the infectiousness in terms of infectious contacts. And then you have phenomenological models which can be deterministic or stochastic and include transmission dynamics models formulated using differential equation or stochastic process. So for deterministic, you call it compartmental deterministic model. And then we have stochastic that are also compartmental in nature. And then transmission dynamics model depend on tacit assumption at the individual level. Now, the development of many new statistical models and methods in the study of infectious disease were driven by the HIV epidemic. So what drove the need to develop more methods in terms of statistical models and method was the outbreak of HIV, especially in the 70s, when HIV started thriving. Now, so data arising from infectious disease investigation pose unique challenges in classical statistical theory and practice, because disease outbreak data do not arise from design experiment. Now, when an outbreak is going to happen, it's not something that you design. It's natural phenomenon. When COVID came, it was natural. It's not something that is like a lab that you culture. You say that you are introducing some virus into a particular mouse, and then you are testing the placebo and all of that. That's not the way disease happened. Now, the way COVID happened then, you cannot repeat it. We cannot repeat it artificially. Do you agree with that? We can't. So outbreak are not something that you can design like an experiment. That you go and buy your rats and then you introduce something into their system and you keep them for some time and you are watching them. Those are lab work. But when it comes to outbreak, they are natural things, and then so each outbreak cannot be repeated naturally under identical conditions. So whereas the large amounts and multiple sources of clinical data, outbreak investigation data from non-conventional surveys, public health surveillance, and observational data from prevalence and incident cohorts are collected addressing the same outbreak events. Now, you see most of this malaria data that we are even talking about, they are collected from like primary or both public and private settings, hospitals. For each of those states, in all the local governments, they will bring it together, and then the state will collate it. So both from public and private. I think when we came here, some people were saying that at the hospital here, they have some data for Benue State, and we would like to see it. We want to see those data. So before statistical methods are used to understand and control the epidemic, statistical models are needed to address the data generation processes. They are required to address the data generation processes, which not only include the epidemiologic, biological process that give rise to the outbreak, but also the process that dictate how data are observed and how a case is documented and reported. Now, that one is another story for another day, because when it comes to case reporting, it's a that's another terrible thing in Nigeria. And one of the things I advocated for in my last meeting last week was the fact that now, if you are telling people to go and get reports, surveillance, and all that, people should be motivated. Now, those people who are doing this job, they are low class workers, and if they are not encouraged, they will bring out bad data. Now, somebody went to the hospital, he was showing some symptoms, and because they have asked them that they should record anything that comes as malaria. So she recorded it as malaria, even though the child was not having malaria. So when talking about fitting models to data, so we tend to think of one type of model design for a specific purpose. However, fitting a dynamic mathematical model to observe outbreak data, e.g. for the purpose of estimating important transmission parameters, involve all three levels of models. One, the population phenomenological model, which depends on the tacit assumption of the individual-based model nested within it. Now, what we are saying there is that for every mechanistic model, compartmental model, there is an individual-based model that is nested in it. Now, it's because we have the understanding of the individual level of transmission that led us to the population-based model. We saw that one person was infected, and then one person infects at least two persons, and then the transmission tree started growing exponentially. So now and also the statistical model that links the disease transmission process to the data generation process. So now there is a statistics aspect, and also there is what? The mechanistic aspect, which show the underlying nature of the disease dynamics. Okay, so we have the statistical models. Now, statistical models are data driven, and without data, you cannot carry out the statistical model. Now, they explore correlation and understand the trends and patterns in data. Now, so another thing is also that with statistical model, you can identify seasonal patterns, seasonality in the data, and all that. And then you can also carry out regressions by showing relationship between two or more variables. Then with statistical, now time series seems to be a statistical model, but it's a subject of its own, on its own right. Time series is a discipline on its own. So it can be used for nowcasting, like I said this morning, and forecasting. So statistical model can be used for you want to check correlation. Like correlation has to do with association. Now, and regression has to do with relationship. So there are two different things. You can be associating with somebody and you are not related. Yeah. In terms of you are staying in the same house, you are neighbors, but you don't have any relationship. So when it comes to regression, it's stronger in terms of analysis of statistical models. So when you are checking regression, okay, it's okay now. So you are checking regression, you are trying to do a stronger thing, a deeper thing than just correlating. So correlation is just showing association. So now these are two different things. So forecasting to predict the current epidemiology and where it might be in the next few weeks. Now, forecasting is a means of prediction, but it's just that it's limited within a certain time. Statistical model may also be used to estimate the efficacy and effectiveness of current treatment and prevention measures. So dynamical model uses mathematical language to describe. So another type of model is, and I told you that what determines the kind of model you are using is the question you want to answer. So you cannot just say, I want to use this particular model. Now, when you don't have a question, you don't know the kind of model you should. So you must know what question are you trying to address. That kind of give you the kind of model you should use. So dynamic model uses mathematical language to describe, can you see now, the underlying biological and behavioral drivers of disease transmission. Underline that word. Underlying biology that statistics does not show. The statistical method does not show the underlying biology because it is functional approach, surface level thing it deals with. Now, if you want to go further to see the underlying biology and behavioral drivers, what are those things driving disease transmission? How do you see them? You see them through a mechanistic model. Now, mathematical models, once validated against historical data, can be used as a tool for scenario analysis. So you can subject them to different scenarios by, okay, if I use 10% LLIN, you see the curve. If I use 20%, 30%, 50%, different kind of strategies. And then you are seeing a lot of things going on, and you are able to come to an optimal result. The one that is averting the cases most, you pick. So scenario analysis provides evidence to support policy making. So you carry out scenario analysis as an evidence. So that's why, having used the data, you are carrying out an evidence-based modeling output, allowing the exploration and comparison of options for interventions against a disease to support decisions aimed at controlling that disease. Now, what do we do in mathematical model or dynamic model? We simulate processes. Can carry out simulation. Now, it could be deterministic. Dynamic model could be deterministic. That means there is no random. No random is involved. No randomness. It could be stochastic. So if it's stochastic, you are exploring outcomes. Like the one I plotted the other day. I'm going to show another curve now. You want to obtain a distribution of the outcomes. Each of those outcomes, whether it's normal distribution or Poisson or anything. Then randomness is important when it comes to stochastic model. And then metapopulation and network is another type of dynamic model. And then we have an individual or agent-based model. Now, we also have discrete models that deals with discrete countable set of numbers. Not so much, not like a continuous. The one we are dealing with that is continuous. But this one, when you say discrete, is the numerable. So you see, use all numbers and then rates converted to probabilities, then the possibility of disease eradication. Now, the stochastic model, you see here now, you look at it. If you look at as at day 5, you look at the number of people that have been infected. So day 5, if you use this and then you cross it to this side, you discover that maybe this one should be around 50, right? So between 0 and 50 people have been infected. So it's giving you an interval. Like I said yesterday, stochastic gives you an interval. Look at the number of simulations. So the number of infected cannot just be fixed like points. You have an interval. Then the metapopulation. The concept of metapopulation does not originate in epidemiology but in ecology, where you have what's a metapopulation? It's a group of population of the same species that live in spatially isolated areas but interact on some level. So metapopulation occur when different populations live in fragmented habitats but are connected through migration. Now, there are different ways metapopulation can happen. We have temporary, we have permanent. Now, temporary in the sense that you are living in Nasarawa, but you are working in Abuja, and you commute between Abuja and Nasarawa every day. You have to capture people's movements. Are you getting what I'm saying now? Now, these are temporary one. We have long-term one in terms of something happened in a particular location. When we are coming down to Benue, we go to certain places where there are IDP camps. So some people migrate because there are crises in their environment. So they migrate to such location. So we also capture that in terms of population movement, because those are drivers of sometimes seasonality we are seeing. So in metapopulation, you want to see things at the spatial level, not just at a temporal level, mathematically in a dynamic model. So in statistics, we call it spatiotemporal models, but in mathematics, we call it metapopulation model or spatial model. Sorry. Now, the spatial model that you are using statistics to do, we are using metapopulation to capture it. It's a concept in epidemiology. So I'm going to be talking about this mathematically in one of the classes later on mathematics, the modeling. I will use some examples how you can model metapopulation. Now, using metapopulation model. So this one, metapopulation epidemic model, consists of n patches. You see how people, now you see the network of people, and then you have n patches. Maybe n patches can be just 2 locations, can be 3 locations, can be 4 locations, depending on, can also be 36 states in Nigeria. We want to look at how the spread of malaria, especially in the whole state in Nigeria. You can also do that. So it is defined, the population of each patch is assumed to be homogeneously mixing. What do I mean by that? Homogeneously mixing is that we assume that everybody is the same. You understand? We are not looking at age. We are not looking at whether they are male or female. Everybody is the same. That's the assumption here. And then it's divided into the typical epidemiological classes, SIR or SI. And then we are looking at them at population level. Network model track the network of contact between individuals. Infection can occur only between infected individual and subset of the total population with which they are in contact. So for network models, if this guy is in contact with this population, they can get infected, and then, people in your network can infect each other. Now, individual-based model, you see now, every individual, they are scattered there. Each person is being modeled, is an agent. So this track what happens to each individual in the population, each person. You, as an individual, what happens as far as the disease dynamics. So it allows chance to determine, that means you put randomness, stochastic fluctuation, whether or not they could become infected and infectious at each time step. So at each time step, can this person, if he's in contact with somebody who has the disease, will he be infected? So in that case, we are putting in probability. The probability that this person can be infected or cannot be infected. Each agent or important group assign a compartment. So each person here, each of us, we have one compartment. So if we are 1,000 here, so it means that we have like compartment like that. Each person have his own compartment. So, and that is computationally intensive. Now the number of compartments can increase exponentially. You know what that means? So that means e raised to power something. So you know what that means. So if I say e raised to power 100, that means 2.7 something raised to power 100. You know what that means. So that's very heavy. Each agent has a set of attributes, e.g. vaccination status. maybe you are looking at vaccine preventable disease like measles, or rules are set for how agents interact. So you set rules. So in your algorithm, you already set rules that how does people interact. You set it so that that will guide your simulation. So your own agent-based model may be different from mine, but what comes out is what is the output you are getting. We also have the health economic models. They are used primarily to explore the potential costs and benefits of health interventions. So after you have done all your mechanistic models, dynamic model, there's an health aspect, health economic aspect, which deals with exploring the potential costs. So this thing you are saying, this scenario, you are saying if we use 80% LLI, what will cost the government to do this kind of project? If they are doing it, now if we use 80% or we use 60%, what is going to be the cost? So they'll begin to compare in terms of resources allocation and all of that. So, and then look at now, this is a graph for us. Now, statistical model, how much complexity do I need? Now, the simplest out of it, if you look at the x-axis here, you find out that as they are going down, as we are going down, as you are getting more complexity, you are having increasing realism. Now, the more complex a model is, the more realistic it will be. But the challenge is the more decreasing it will be in terms of tractability. It's difficult to track because you are putting a lot of parameters, a lot of things are put together because you want to provide a realistic situation. So you start from univariate linear for those of us who are doing statistics. Univariate linear, just one variable. You understand? Those are very simple ones. Then you go to multivariate linear. Then from multivariate linear regression or anything, you use generalized linear. And then you move to generalized linear and mix. So from here, as you move down, the complexity is increasing, but the tractability is decreasing. Now, for dynamic model, how much complexity do I need? Deterministic model, continuous and discrete. Now, we have said the other time, deterministic models, that's compartmental models, is the least, is the simplest. And then you move to stochastic models. So we are saying increasing complexity and realism. As you go down, complexity is increasing and is getting more realistic. So from statistic model, we move to better population and network. From there, we move to agent-based models. So, but it's decreasing in tractability. Now, how good is my model? A good model should be parsimonious, yet realistic. A good model should be what? Parsimonious, yet realistic. A good model should conform to data. A good model should conform to data. A good model should balance conformity to data and parsimony. A good model should be easily generalizable. A good model should be validated. Validate model and make predictions. Right? So if you are saying, oh, my model is good, is it parsimonious? That means, is it simple? And not so simple as to remove the details, realistic things, and then yet realistic. Then does it conform to data? Does it balance conformity to data and parsimony? That means striking a balance between conformity to data and being parsimonious. And then is it easily generalizable? Now you have developed this model. Can you also use it to capture another dynamic or systems, and then you are getting some predictions? So when we talk about validation, we are talking about now you have developed the model, you have been able to picture the scenario analysis, and then you are now saying, coming back to the real world, what you have modeled, does it represent what is going on in the real world? You have to ask yourself this question. And then finally you make predictions. Make predictions. Can you use it to make predictions? Okay, my 40 minutes is over. Thank you very much.